Sure, that gives everybody flashbacks to when the COVID happened.
Right.
Yeah.
I think you're right. Okay. Well, we should start. Okay, so I said we would look at our worksheet problem. Yeah, remember? Okay, so we had a worksheet problem, and let's get a new layer.
We'll make sure to turn. Yeah.
Oh, TV's not on yet. Thank you. I always forget that. Ready, time to adjust.
Copy the notes down the CD.
That'd be fun, right? Yeah, man. Okay. So we have, this is the last part. Let me move this Zoom thing. If I can, grab it. All right, so we have a thick slab. From z equal negative a to z equal a carries a uniform volume current which is just J equals, some magnitude in the X hat direction. And we want to find the magnetic field as a function of Z. Inside and outside slab. Okay, let's draw a picture if we can. It's kind of hard. All right, so you know how it is, pictures. Okay, so I'm going to put the z-axis up like this. And then the slab is basically at z equals plus a. Yeah. And z equals negative a. Okay, so basically, and it's coming, let's let it come out at us in the x direction. So the x direction is like this, yeah. And then the y axis will be here. We have plus y and negative y this way. Yeah, does this make sense? And then, slab's got some sides to it. Okay, so the current basically is just coming out of the board towards you. Yeah, so we can also draw the current like this, or just without the little, you can do that. It might be a little cleaner just to leave off the little circle, which I usually put on to mean a vector pointing out. But let's just put out, these little things. Current, uniform volume current. It's meant to represent the current coming out towards you. Okay, so what we're going to do is we're going to put an Amperian loop, right? And it's kind of like the similar thing to a Gaussian pillbox, right? If we have a slab of charge, right, with surface density or something, we use a Gaussian pillbox. It's the same kind of idea that you're going to put a loop that is perpendicular to the current. So the current is going to go through the loop, right? So it makes sense to put one here. And the easiest thing to do is to put one so that one side of that loop is on the z equals 0 area. I'm sorry, line, right? Okay, so let's do that. And we're going to put that in pink. So let's do an Amperian loop that's going to be start kind of here. It's going to go up a distance z, and then it's going to come back down. Okay, so this is our Amperian loop. Remember, you always want to make an Amperian loop that you think one, you'll have some current piercing it, right? And two, if you're gonna use Ampere's law to get the B field, then you better be sure that you can figure out that the B field is constant on the parts of the loop that you care about. So, okay, right? So like in the Gaussian pillbox example, the E field was constant along the top and bottom of the pillbox, right? And then the sides, the E dot dA was 0, so we didn't care, right? Okay, so this is going to be a distance Z. Okay, because we want this as a function of Z, and we'll make this L long. Little L. Okay, so now we've got to just think it through. Now, first of all, I need to write the direction of my integration, right, around the loop. So remember, you put your thumb in the direction of the current, your right hand, thumb in direction of the current. For me, coming on board, it's this way, but for you, it's this way, right? And then you curl your fingers in the direction that you're going to write your arrows for going around the loop, right? So that means that our arrows are going to go like this, aren't they? Yeah, so we're going around. Okay, fine. Now we got to think about the direction and all that stuff. Okay, so for positive Z, so let's say we're on this part of the loop. We know that B should, let's think about what would B point in, right? So B is going to point in the negative Y direction, right? This way. Everybody get it? Yeah. And then, but below Z, for negative Z, it's going to go in the positive direction. So this means at Z equals 0. So this tells us that at Z equals 0, B equals 0. Okay. So that's great because that means one leg of our Amperian loop we don't care about, right? Okay. All right. And if B is pointing in either plus or minus Y, right, then B dot DL for the sides is 0. Yeah? You get it? Okay. So we really only care about that top line. Yeah? Okay. So we only care about top line. All right. So we know Ampere's law, in integral form is B dot DL is equal to mu 0 I enclosed. So let's work on I enclosed first. So I enclosed. Well, let's see, how would we do that? Right? Remember what it looks like, right? It's the integral of J dA. Oops, my bad. Yeah? Well, J dot dA, I guess I should write that, be more clear. Okay. Over a surface that's bounded by your Amperian loop in pink. Yeah? Okay. So what do you think dA is in this case? We're in Cartesian coordinates, aren't we? What's changing as we go along the loop from on the top part of the loop?
Y.
Okay, y is changing. Good. So we know we're going to have a dy in there. What else? Is there anything else? No, x isn't changing. Right. So z isn't changing, but it's just going to be z dy, right? There's no dz because z is not changing. Does that make sense?
Yeah.
Okay. So this is going to be just the integral j dA because dA points out of in the same direction as that current, right? In this case, because the current is along the x-axis, right? dA is also along the x-axis, right? So, okay, that's great. And then this is just going to be z times the integral from 0 to L, right? Of j. Oops, j can come out too. And so we just get z, j, L. Okay, fine. Now we just got to do this part. Okay, so we know along that top route that dl is going to be dy, right? And that b is constant along that line. Yeah, so we're going to have the integral b dot dl, oops, dl, b and dl in the same direction, so this is just b dl, and this is just the integral, b can come out, dy from 0 to L, and so it's just BL. Okay, putting it all together, we get BL is equal to ZJL, right? Oh, I forgot my mu 0 times mu 0, okay? The L's cancel out and I get B is equal to mu 0 JZ. And we have to say whether it's, right, now to put a vector nature to it, right, then we can do it a fancy way or not fancy way. I prefer kind of not to do it the fancy way, but you can say this is y hat direction, right, for negative z, and y hat, and negative mu 0 j z y hat for z greater than 0. Yeah, that makes sense. Okay. All right, so that's how we use an Amperian loop for that. All right, so let's move on. So we are going into 5.4. Okay. By the way, I have to end a little early because I've got to go set up Zoom for our super class. And if I end at 12:10, there's no way. Because I already told the speaker that it should be on by 12:10. Okay. All right, so we're going to do section. And there's a video on 5.4 on the whole thing. So if we don't finish it, we don't finish it. Okay. Okay. Okay, so let's just review. Let's compare electrostatics and magnetostatics. So electrostatics, we have two Maxwell's equations. Del dot E is equal to 1 over epsilon naught rho. This is Gauss's law in differential form. And an equation that tells us that the curl of E is 0. This doesn't have a name. No name. Yeah. Okay. And now for magnetostatics, we have two equations. We have the del dot B, divergence of B equals 0. This does not have a name. Although some people may call it no monopoles, no magnetic monopoles, right? Because the direct consequence of this is that Maxwell's equations predict that there are no magnetic monopoles, as we discussed, right? It doesn't mean that they don't exist somewhere and Maxwell's wrong, but people have been looking for them for a long time and no one's found any. Okay, and then the next one is del cross B equal mu 0 J, and this is Ampere's law, as we've seen in differential form. Okay, they've kind of got the symmetry going, right? Okay, and then Well, so one way to talk about this is that electric fields diverge away from charges, from positive charges, right? And magnetic fields curl around currents. So it's this, this kind of symmetry where one is curling and one is diverging. Make sense? Okay, interesting. Okay, let's talk about the magnetic vector potential. So we mentioned before that this was common, right? So in electrostatics, right, we had because del cross E equals 0. So because and right, curl grad. This isn't the best way to write it, but maybe I should write it like this. Curl grad equals 0. I mean, if you take the curl of a gradient and the gradient can only work on a scalar, you get 0, right? Always, no matter what you're taking the gradient of, right? Okay, because those two things are true, we can write E is equal to negative del V, right? Where V is the scalar potential. Yeah, remember that? Okay, so really for the same, for a similar reason, because the divergence of B is 0, right? We can write the divergence, sorry, we can write B as the curl of a vector potential. Okay, so we can write for magnetostatics, B, oops, sorry, I meant to write a B there when I wrote this. Okay. We can write B is equal to del cross A, where A is a vector potential, actually, the vector potential really is, so this is the only one you're going to hear about probably unless you go to grad school. It's a vector potential. So unlike V, it's not a scalar, it is a vector, which makes it more of a pain in the butt, right? As vectors are, but there you have it. Okay, so one thing to notice is that we can always, so if we're going to take the curl of B, so let's look at the curl of B in this case. We're going to go curl of B. Well, if I write it, curl of A, right? I'm just substituting in for B. I get by, there's big long formulas. And I'm just shortening it here because del dot B is 0. Anyway, so we have the gradient of del dot A, right? And then minus del squared A. Okay, I'll explain what del squared is. And remember, that has to be mu 0J. Now, because this is the gradient of this scalar, right? We're actually free to just call that 0, del dot A. There's just no reason why we can't call that 0. So we're going to set del dot A equal to 0. Okay, so what that does is give us an equation that looks a lot like Poisson's equation. Okay? Oop, I went the wrong direction. So it's really Ampere's law, though, just FYI, right? So this gives us another version of Ampere's law that looks like this. Okay. And remember that we had Poisson's equation in electrostatics. So we had del squared phi, del squared V is equal to negative rho over epsilon naught, right? We had that in electrostatics. So it looks a lot like that, except for it's a vector. So we have this del squared acting on a vector, which is weird, but I'll explain what that means. But it means we can immediately write down an integral form for the solution, just the way we did for V. Except for now we have like vector stuff. Okay. So let me get a new layer. Are you good, everybody? Okay, so let's just explain what del squared, what does del squared A mean? Well, it's del squared acting on AX times X hat plus Y hat times del squared acting on AY plus Z hat times del squared acting on AZ. So a little weird, right? And remember what del squared is. It's a scalar differential operator that looks like a second partial derivatives. But it is a scalar, right? But notice that what you get out of this is a vector, right? What you get out of this is a vector, right? Okay, so, but by analogy from the way that we solved, used an integral to solve for the electrostatic potential. So if you remember from del squared V is equal to negative rho over epsilon naught. We wrote down V is equal to 1 over 4 pi epsilon naught, the integral rho of r prime d tau prime over omega, right? We can do exactly the same thing from our del squared A. So, and so because Ampere's law becomes del squared A is equal to our negative mu 0 j, right? Now we can say, oh, okay, A as a function of R is equal to mu 0 over 4 pi, the integral, the vector J as a function of R prime, as we know it is, d tau prime over omega. So it is the same except for, and we don't have a scalar charge density, right? We have a vector current density, right? So it's very similar. It's just that currents have direction, charge densities don't, right? Okay. Most of the time you don't really use this, although you certainly can, as we've done many times to get, this is kind of the Biot-Savart law. It's a little bit simpler, right? Because it doesn't have a cross product in the integral like the Biot-Savart law does, right? And then once you get A, you can take you can take the curl to get B. Anyway, and this is the general form with a volume current, of course, if we had A of R prime, if we had a line current, we would have, you know, I. Oh, we always write it like this. Sorry, bring the I out. It's always steady. And then we have DL prime over omega, right? This is a line current, or a surface current, of course. But the vector nature is contained in the current density, right? Because that is a vector quantity. Yeah. Okay. Let me see. I have to get to another folder here, I think. Let's see. Let's see. I'm gonna do that? No, not really. Yeah, maybe I'll do it I'm just gonna set it up. I'm not gonna do the integral though. Hopefully. All right, so let's actually do a problem we've done before when we used Biot-Savart law to get B for this particular situation. But I'm gonna get A. Okay. All right, so we'll put a wire on the z-axis. So the wire looks like this. Okay. It is a wire that goes from Z1 to Z2. Okay. And it has a current I flowing in this direction. Okay. So let's calculate the vector potential. All right. So we have A of R is equal to mu 0 I over 4 pi. This is a line current. The integral dl prime over omega. Okay, fine. So we can set up our coordinate system. So we already have z down, but I'll just kind of, right, like a y and an x. Okay. So let's go out, let's pick a field point. And we're gonna look at just some random point, right? Yeah. So if we look at some random point, let's put that out here, okay? And then we have well, let me move this for a minute because I feel like nope, wrong color. Might do that because it's just in the way. And I think this is also in my way. I'm here, okay. And so we'll have a little, we'll have an R going out to the field point as usual. Yeah, we'll have an R prime that's going to go out to a current element, which is going to be right here. Okay, so we'll have an R prime. That's in pink. And we'll have an omega, which will be in green. That's going from here to here. All right, omega. Okay. All right, fine. So we can use the pedantic approach as usual, which I prefer. So we're going to write down R prime. Well, R prime is just z hat, right? That's easy. R is just in the direction R hat, right? Yeah. So we can say, all right, R is just R hat. Yeah. And omega, just in green, is of course R minus R prime, and that's going to be R hat. Now we'll change all this to Cartesian and or whatever later. And then minus z hat. I guess I should have color coded that, but okay, I'll just leave it. Okay. Yeah. All right. And then dl prime. Let's look at dl prime. Right? That is points along the current, right? Just along the current. And that's going to be z hat. Yeah, it's pointing along current. Okay. So we need the length of omega, which we can write down. We might as well use Cartesian, spherical coordinates since we have an R in there, right? So we can change our R. So first of all, let's just write down the length of omega in terms of R, and then I can change it. So I have omega. I'll do omega squared for now, just so I don't have to carry around a square root, if that's okay with you. Okay, so this is going to be, well, hold on, one more thing. I want to do one more thing. Yeah, so I need this to be in terms of x hat, y hat, and z hat because I have that z hat sitting there. Does that make sense? Yes, okay. So I know that the x component, let's write down R, is R sine theta cosine phi x hat plus R sine theta sine phi y hat plus r cosine theta z hat, yeah? Okay, cool. So that means that, and this thing here is r, right? The whole thing is r. Yeah, okay, so let's write it down. So we have this stuff, r sine theta cosine phi x hat plus r sine theta sine phi y hat plus r cosine theta, and I'll do this minus z all times z hat, right? Now that's our omega. Everybody agree? And now we're gonna get the length squared. I'll take the square root later. I just want to write it all down. So I got a square root term here. So r squared sine squared theta cosine squared phi plus r squared sine squared theta sine squared phi plus r mine, oh, sorry. Okay. Do you mind if I square this out real quick? R squared cosine squared theta plus z squared minus 2rz cosine of theta. Okay, a little simplifying. We get r squared sine squared theta here from these two terms plus r squared cosine squared theta. Oops. And then we get plus z squared minus 2rz cosine of theta, which reduces to r squared plus z squared minus 2rz cosine theta. I want you to notice that the pedantic approach got us to where we would have gotten if we thought about the law of cosines, right? Does this make sense? And the angle between r and r prime. Yes? So this right here is theta, spherical coordinates, yeah? So pedantic approach will get you where you would have gotten already if you just thought about the geometry and applied law of cosines. You have to apply law of cosines because it's not a right triangle. It's your only choice to get the length of this side of the triangle, right? Is law of cosines. Everybody good with that? Okay. All right. So great. That means we can set up the integral. I'm going to erase some stuff. I'm not going to do the integral because I really don't feel like it. So A is mu 0 I over 4 pi. And then we have the integral dz. We just pull the z hat out here. There we go. Over the square root of r squared plus c squared minus 2rz cosine theta. Yep, there you go. So you would just look up the integral and you would do it. Okay? Makes sense. Okay, we'll do another example in a little bit. I can't remember what we're gonna do that example. We're gonna do another example. Thanks. What am I doing to do that? So, give me 1 second. I want to think what I want to do. So, let's see. All right, so how about this? We have I don't know if I really want to prove this right now. Well, Yeah, I'll just write it down. All right. So we'll do another example, but here we're going to get this after knowing what B is. But we're not going to go directly from A. We're going to know what B is and try to get A. Okay. All right. So we're going to look at a magnetic field. Okay. Flowing, sorry, from current flowing down XY plane, infinite plane, right? So the whole plane. And this is, again, this K equals some constant times X hat. So it's only flowing, it's like it's, if you were going to draw your Amperian loop or something, would come out towards you, right? If you're drawing around the where the x-axis is coming towards you. Okay. Now this is very similar to our slab that we just did. Slightly different. You would use the same kind of Amperian loop, and what you would get, so we're just going to state this, you can prove this to yourself, is negative mu 0 K over 2 y hat above plane and positive mu 0 K over 2 y hat below plane. Okay, and we want to know what is A, okay? Okay, so our question is, what is A that would give this B field? Okay, one thing to notice, because we know that A looks like this, mu 0 I over 4 pi, oops, hold on. I should write the one for surface current, right? So A is going to be mu 0 over 4 pi, and then the integral of K, right? dA over omega. Okay, so A is parallel to K. So A only goes in the X direction. It can't go in any other direction, right? Notice that K goes in the X direction. Therefore, A only has an X component. By that? Okay, we know that del cross A must be B, right? So let's just look at a cross at the curl in the cross product form, right? So in our determinant, just the heck of it. So we have X hat, we'll have a Y hat, we'll have a Z hat, and we have del X means partial X, right? Del Y means partial Y, and this is partial Z. And we know that A only has an X component, right? And this will be 0 and 0. So that would be del cross A. This would be B equals, right? Okay. Well, we can actually write this out. So we see that we get, if we cross out the X hat and the Y hat, we get 0. So there's no X hat component to this. Obviously, B doesn't have an X hat component. You following me? We have 0 times X hat. And then we have, so we cross out the Y and the Z, we get a negative sign. And then we get, this is 0, so del X on 0 is 0, but then we get minus del Z on AX. So partial AX, partial Z with a negative sign, which gives me another plus. Okay. Therefore, I now have a differential equation for A, because B, right? So we can do this in steps, because we know B above the plane. So we'll do the one above the plane first. So let's look at above the plane. Okay. So above the plane, we're going to have B, right, which is negative mu 0 the constant K over 2 in the y hat direction, right? Is equal to the y hat times partial A Z partial Z. Yeah? Okay, so those y hats can go away. AX, sorry, not that. Okay, okay, and so this gives me A is equal to negative mu 0 K over 2 Z, right? If I integrate it. Yeah, okay, that's above. And then below, same idea. We get positive mu 0 K over 2 is equal to partial AX partial Z, giving AX, oops, this should have been AX here, sorry about that. AX is equal to a positive mu 0 K over 2 Z. Yeah, this is above. And this is below, so I could replace the whole thing as, I could say this is A, I'll put it here. A is equal to mu 0 K over 2 times the absolute value of Z in the X hat direction. Is that right? So when Z is positive, no, I need a negative sign. Shoot, there. Yeah. Yeah. All right. Cool. Or let's keep going. So just like we had electrostatic boundary conditions, we have magnetostatic boundary conditions. Okay, so let's look at E. So we'll recall that E was discontinuous at a surface charge we had E above, like if you think of an infinite plane of charge or something, right? So, or a sphere of charge, and above the sphere, right? E plus, oh, sorry, this isn't plus, this is perpendicular. So the perpendicular component minus the below perpendicular component of E, okay, perpendicular to the surface, is this discontinuous thing, right? So it's proportional to the surface charge, 1 over epsilon naught surface charge, right? But the parallel components were not discontinuous. So parallel to the surface, they're equal. Right? The E's parallel to the surface were equal. We really should have vector signs, but okay. Okay. Now B is discontinuous at a surface current. Okay. So B is discontinuous at a surface current. Okay. But it's a little different. Okay, of course B is going to be different, right? So the perpendicular components above and below are equal, not discontinuous. It's the parallel components that have a discontinuity. Proportional to the surface current K. Okay. And we can write this before we also wrote this, the discontinuity equation for E. Where did it go? Okay. We wrote it in a vector form. We can also do that here. It's not the most exciting thing, but you can. And one way you can do that is you can say, okay, vector b above minus b below vector is equal to mu zero surface current vector crossed into the perpendicular, the vector perpendicular to the surface. Remember, n was that vector perpendicular to the surface. Okay. So does this make sense that this would give you those two things above? Is it the way the cross product works? Yeah, okay. All right. All right. And also we had conditions on the vector on the scalar potential in boundary conditions, similar things here with A. We'll have some boundary conditions for A. So let's write those down. So A above is just equal to A below, but the derivative is discontinuous, just like we had before with the potential. So the derivative along that perpendicular vector, like the directional derivative, and that's proportional to negative mu zero times the surface current. Okay. All right. The next thing we want to look at is, just like we did a multipole expansion for the scalar potential, we would like to do a multipole expansion for the vector potential. Okay. Right. And we'll use a lot of what we already know how to do from that discussion. I can't remember what it was like 3.5 or something, that section. All right, so we'll do multipole expansion for the vector potential. Okay, and this is a power series in 1 over R. And if R gets large, then of course the series is dominated by the lowest orders, like 1 over R, 1 over R squared, right? As R gets really big. So this is when you're far away from, your currents, right? The farther away you are, the better your multipole expansion is, if you're only taking a few turns. Does this make sense? Okay, so remember that this is a power series. Expansion in powers of 1 over R. Okay, cool. Oh, I keep going the wrong direction. So we for electrostatics, we found actually that 1 over omega, so we found 1 over omega, if we expanded this, right, we got 1 over R times the sum from n equals 0 to infinity of R prime over R to the n, and then these Legendre polynomials in terms of cosine of theta prime. If you don't remember that, go back to the previous chapter. We did a lot of work to get to here, okay? So we can literally just write this down, okay? We know that A of R, okay, is going to be, for, let's just say, a line current. This is good for any other kind of current too, but. Okay, and this is going to be around a loop, right? 1 over omega dl prime. Yeah. Okay, so we're going around a loop, right? An Amperian loop in this example. And then we can rewrite this now because that 1 over omega has this expansion. So I have mu 0 I over 4 pi. And then I can remember we brought the sum out of the integral before when we were doing this. And we get 1 over R to the n plus 1 by kind of absorbing this guy. outside of the integral because he doesn't need to be in there. And then this is the integral around a loop of r prime to the n p n of cosine theta prime dl prime. Okay. And just to write out the first couple of terms, we get mu 0 I over 4 pi. And then the first term is the 1 over the n equals 0 term, so 1 over r. And this becomes the integral, and the n, when n is 0, p of cosine theta prime is just the function 1. Okay, so, right? So if you're just writing your Legendre polynomials p of x, pn of x, right? P0 of x is just 1. Okay, so this means we'd be integrating this dl prime here. And then the next term is the 1 over r squared term. And this is an integral of r prime cosine theta prime because P1 is just cosine theta. Okay. dl prime. And then plus one more term. I'll just write one more term. R cubed integral r prime squared 3/2 cosine squared theta prime minus 1/2 dl prime. So it's very squished. And then it's plus dot, 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 right? Because this goes on forever. All right. But we're pointing these out for a reason because this guy is the monopole term. Right? The monopole term goes as 1 over r. Then we have the dipole term. Then we have the, whatever this is, right? Quadrupole. Okay. Now, let's look at the monopole term. The monopole term is the integral around a loop of d of a vector quantity. Right? So if you go around a loop with dl, it starts out, let's say, in this direction. If you go all the way around, it comes right back to this direction. And it's 0, right? So this monopole term is 0, which we should expect, right? Even though this, your A may not be 0, right? The monopole term is going to be 0. Does that make sense? So the dominant term always for magnetic vector potentials is the dipole term. It's the term with the lowest power of 1 over r that you can actually have. Yes? Okay. Okay. I think that's all we need to do. Yeah. I can actually stop this recording and actually let it process before I go.